All right, welcome back. We're in section or module 4.3a, comparing quantitative data across groups. This is a short one, so I'm going to combine that with module 4.3b in one video. So let's dive in. 4.3, we're now comparing quantitative data across groups. So, excuse me, there's not, like I said, there's not a whole lot of anything new in this 4.3a. It's very short. You just kind of need to be able to look at some histograms, box plots, and compare the two things. So let's look and start with the motivation here. And there it is. So to pair this quantitative data from two groups, right, what we're going to end up doing is looking at things. My 10 working. The difference between two means, the mean from group one minus the mean of group two. We're going to do some tests to see if there really is a true difference between two groups, right? Now this is often found in studies and experiments and things like that. So we're going to have to identify which conditions satisfy being able to use the t-distribution with the point estimate of the difference of the two means, right? Which is to say, we want to find out if population 1 is different from population 2 by some significant amount. We're going to go sample population 1 and get a sample mean from population 1, x bar sub 1, and look at population 2, get some sample from population 2, and we're going to look at the difference between those, and then of course see if that is significant. For now, this 4.3a doesn't go into the math of it. It just goes into the motivation of it more than anything, and what it looks like. So we've got some information. Let me grab, what is this from? Should have grabbed this with it. Oh my God, why do you do that? That drives me crazy. There we go. So we have two bits of data. On the left, we have a bunch of numbers from a country that had a population gain countries. So there's random sample of 50 countries, or sorry, not 50, 100 countries that had a population gain between 2000 and 2010. And on the right, we had the median household income from 50 countries that did not have a population gain, right? So we separated the two groups based on whether or not the country's population was increasing or whether it was not. And then we collected information, in this one specifically, the median household income in thousands of dollars, right? And so they ask a question here somewhere. The question is there a difference? It's a notable difference. All right, well, I chewed up the word difference there, and the answer to that is, how the hell would I know, right? I don't know. There's a whole bunch of numbers. There's a whole bunch of other numbers. No idea, right? It's hard to determine anything from just a big list of numbers. So what they've done is, and they didn't use this data, which is weird. This book drives me crazy. I hate this book. But they used a different set of data. Let me move this up. And get that. A different set of data, but the same kind of idea here. This is 2 box plots from medium income, but this is from population gain countries versus population not gain countries. But this is data that was collected between 2006 and 2010, right? And so it's not the same data, right? That's the first weird thing, is it's the same idea, but it's not the same data from above. Stupid. The other thing is I don't know what these dots are, right? So typically on a box plot, if I had a whole bunch of data that fit nicely into this box plot, my low, my high, wherever that box plot, was skewed. But if I had, like, say, I was making a box plot for median income of people in the US, right? I don't know. And I just randomly selected a bunch of people, and we've got on the poor end of it, in a year, I don't know, somebody's making $20,000, right? And then on the high end of it, I don't know, a couple of lawyers came in and they're making $200,000. But also Jeff Bezos happened to be in my sample. His value is going to be way the hell over here, right? And I'm going to put it as a dot and not extend the box plot because he's an outlier in this data. If he's clearly way out in left field to the rest of the data, I'm just going to put a dot there to say, no, this guy's an outlier. But if you have so much damn information that you have 50 billion freaking dots, those are not outliers. So I don't know what this picture is. It doesn't explain what those dots are. That whoever wrote this book is drunk and whatever. I don't know. I hope they didn't make any money off of it because it's not worth anything. But so we're going to ignore those for now. They don't matter. They don't exist. I don't know what they are. They're not part of the data above. Ignore it, ignore it, ignore it. I don't know what they are. You don't have 80 billion outliers. If there's 80 billion outliers, that's your data. It goes out that far, right? But looking at these side by side, and again, I don't know why they decided that it would be a good idea to put them vertical after we've been playing with them horizontally. And I don't know if I can rotate it. I think I can. Maybe not. I don't know. But we can kind of get some information about these countries. They both have two groups. The left is the countries that had a population gain. The right is the countries that did not have a population gain. Their minimums are about the same. But the max of the no gain countries isn't quite as high as those with gains, right? In fact, if we look at this, the 50th percentile of the countries that had population gain matches with about the third quartile of the countries that had no gain, right? So we can kind of tell much easier with this visual representation, clearly the countries that had a gain in population overall had higher median incomes, right? And we can gather a bit of data about exactly how that difference looks amongst these quartiles and things. So we also, oh, just kidding. I thought they had a histogram, but they didn't. I think it's on the next part. And I might be lying to you because that's just what I do. Oh, they do. So, all right, let's move on from this. That was it. That was 4.3A. Let's roll through. This is now 4.3.B. Yoink that. Oh my God, this scaling is obnoxious. that guy. Okay. So we're going to start, and we're going to, through this section, we're going to end up creating a confidence interval for the difference of two means. So we just jump in with the question. And I'll just post this so I quit having to resize things all freaking day here. All right, the question is, does treatment using embryonic stem cells help to improve heart function following a heart attack? Right, that's our question. That's what we're interested in. Design a study and collect relevant data on the topic. So in an experiment to test the use of the embryonic stem cells in sheep that had heart attacks, I didn't know that was a thing. 18 sheep were randomly, have you ever heard of a sheep having a heart attack? That's the weirdest thing. 18 were randomly assigned to the stem cell group or the control group, and the change in their heart's pumping capacity was measured for each sheep, right? And so that's important that they were randomly assigned, right? 18 sheep were randomly assigned. And the change in their heart's pumping capacity was measured for each sheep. A positive value corresponds to increased pumping capacity, which generally suggests a stronger recovery. So good is a positive change. Right? Or if you want to call it success, whatever you want to call it, that's what they want to measure. Our goal would be to identify a 95% confidence interval for the effect of stem cells on the change in heart pumping capacity relative to the control group. So we're now comparing those sheep that got embryonic stem cell treatments to those that did not. So our data is given to us. Our data contains the summary statistics for the experiment. They've run all these numbers for us. Very nice of them. That's cut into the 9 sheep that received stem cell treatment and the control group, those that did not receive stem cell treatment. And so the number in each one is 9. The mean of each one is given 3.50 and negative 4.33. So we can write this as X bar. They end up writing it as S, what do they do? ESC, experimental stem cell experimental stem cells, I guess. I don't know. You can call it X1, X2, as long as you identify which one is which, but they call it this. X sub ESC, X bar sub ESC is 3.50. That makes X sub control. You can write control out, or you can just put a C. I'll just write CONT. The X bar of the control was negative 4.33, right? And then we would have, excuse me, the sample standard deviation of the experimental stem cells was 5.17, and the standard deviation of the control group was 2.76. So we're just kind of gathering the information that we're going to come back to, again, with this 95% confidence interval. Right? That's the important data. And then, of course, we want to perform our statistical analysis. We get our point estimate by taking the difference of those two values. It's written here, so I'm not going to write it again, but it is the difference between the experimental stem cell group minus the control group, and so that's 3.50 minus negative 4.33, that is 7.83. Now, in order to I can't tell you how obnoxious this cut and paste has become. I'm sure you all know because you're watching this, you're probably getting freaking seasick with how much I have to move this stuff around. Anyway, using the t-distribution for the difference in means, it can be used for inference when working with a standardized difference of two means if these two criteria are met. Each sample meets the conditions for using the t-distribution, and those samples are independent. Right? Now, they've created a histogram. So I mentioned, I thought I saw there was a histogram. Here it is. Visually, pretty convincing that there's going to be a difference, right? So no difference is sitting right there at 0. And for these to be compared, you'll want them to have the same width, right? The same, the number line, the x-axis number line has the same scale, if you will. They both start, your zeros line up, your 15s line up, your negative 10s line up. Otherwise, that kind of doesn't make sense to look at them comparatively. But the control that had no treatment all have a pretty big chunk in the negatives. There's a couple negatives in the ones that receive stem cell treatment, but you got a pretty sizable chunk to the right here. So visually, this is convincing. If you receive something that was completely the opposite of this, you probably would be like, oh, this thing's going to fail. This looks like it's going to succeed. That's not good enough, but it is motivation to continue on with the test, or at least to kind of give you an advanced warning of what is about to happen. Oops. Yep, that's fine. All right. Can the point estimate, which was given to us above, 7.83, be analyzed using the t-distribution? So there's the two criteria that were above. Number one says in the study, they were assigned at random. That's the important part, to either the stem cell group or the control group. That makes this a randomized experiment. The 18 sheep involved in the study are less than 5% of all sheep, probably. I think I've seen more than that many sheep in my life, probably true. So the observation units are certainly independent. And then additionally, they don't show any clear deviations from normality. And so we would then meet criteria number one. And then number two, the sheep in each group were also independent of each other. That is true as well, because in each group they are again less than 5% of the total population. Okay, so there's a new standard error calculation that we'll be using here. So this one should be for your notes. It's a little bit ugly. That looks a little bit shady. I might just have to write that. But the standard error, I don't know if I can write it any better. The standard error for, in this case, I'm going to write it in general. So for x bar 1 minus x bar 2 is equal to the square root of sigma 1 squared over n1 plus sigma squared sigma sub 2 squared over n2. Right. But we don't know the standard deviation, right? That sigma is the population. So because we're using a t-test, then that is x1, x bar 1 minus x bar 2 is approximately the same as the standard deviation of the sample 1 squared divided by n1 plus the standard deviation of the sample 2 squared over n2. And so this is the one that we're going to be using. So plugging these values in, right? So for this, in this case, we're going to use the S version of this thing because that's all we have. So if I plug these values in, I don't have those values in front of me. Let's say I'm just going to copy them from over here and repaste them. All right, so we're calling, where there it is. So S of the stem cell, ESC, they've denoted as the experimental stem cells. So S is 5.17. So that's 5.17 squared over N, which is 9. And then plus the S of the control group, which is 2.76 squared over also 9 from the control N. This ends up being somewhere around so 6 squared over 9. And again, throw these things in the calculator, make sure that you can do this. This ends up being 1.953. I'm going to just round it to 1.95. It's about there. Oh, yeah. They do have it in the book. I didn't see it till just now. Of course, it screws with my sizing, but that is our standard error of the difference of 2. What is happening here? Right, that. Good. All right. So we have our standard error, and then we have 9 in each group. And that means that we have degrees of freedom is 9 minus 1. So the degrees of freedom is 8. Right? We're using a 95% confidence value. So if I grab that chart for the 8 millionth time, I have to scroll down and find it. There's the part that's important to us. All right. So where's my pen? Where is it? Our degrees of freedom are 8. Let me get that highlighted there. And Oh, I know what it is. I would think at some point I could draw a straight line, but I can't. So we're looking for then 95% of the values, right? And we're really just looking to see if there's a difference between those. And so I want those 95% to be in the middle. So we're talking about a two-tailed test. And so on the outside of that two-tailed test is 5% of values split between the two tails. So I'm looking for 0.05. And I find that my T star then at 8 degrees of freedom is 2.31. I can now create my confidence interval using this. I don't know why I keep writing instead of just typing, but interval for the difference of two means is given by, it's still a point estimate plus or minus a margin of error, but that point estimate is that x1 minus x2, or whichever one is, is the larger minus, or the one you're interested, minus the control group, and then plus or minus the T star times your standard error. And we've calculated all of these values. The point estimate, x1 minus x2, was 7 point something, maybe. Was that like freaking 10 days ago? Where is this? I know I wrote it somewhere. Oh, there it is right there. I highlighted it, 7.83. Plus or minus this T star that we just calculated, 2.31, and then multiplied by that SE, which is right there, 1.95. Right. So we just have to do that calculation, do the plus, that's your upper limit, do the minus, that's your lower limit. These guys end up being, the lower limit ends up being 3.38, and the plus, the upper limit ends up being 12.38. So again, what does that mean in context of this problem? We have this. We are 95% confident that the interval of 3.38 to 12.38 captures the true difference between the mean heart pumping capacity for the stem cell group, the mean heart pumping capacity for the control group, or in other words, our results indicate that the embryonic stem cells improve the heart's pumping function in sheep that have suffered a heart attack by somewhere between 3.38% to 12.38%. Because 0 is not in there and there's no negative numbers in there, you can then justifiably say our research suggests that that embryonic stem cell creates a positive change in the heart's pumping function. So let's do a full test all the way through. Okay, here it is, the question. Oh, that's helpful. Awesome. Let me close this. Try again. Where did it go? That's not cool. It's still not working. There we go. All right, it's back. Window, that one, that one. Okay. Yoink. All right. Try this again. All right. There is our issue. So the second research question is involving the difference of two means is there convincing evidence that newborns from mothers who smoke have different average birth weight than newborns from mothers who don't smoke? And we'll answer this question using a hypothesis test. So I'm just going to grab all of this. Can I get it all? Oops, I missed half of it. There we go. Slap it in there. All right, beautiful. All right, so they have collected some data, right? So we need to design a study for this. So it says a data set called Baby Smoke, which these data sets, whenever they refer to that, there should be in the book some actual data set in the back of the book. But it represents a random sample of 150 cases of mothers and their newborns in North Carolina over a year, right? One could argue, since you limited yourself to North Carolina, you can only consider your population mothers in Carolina. But again, we're just going to walk past that one and pretend it's not a problem. 7 cases from this data are represented in table 4.29, right down there. We are particularly interested in 2 variables, weight and smoke. The weight variable represents the weights of newborns, and the smoke variable describes whether or not the mother smoked during the pregnancy. We're going to use the North Carolina sample to try to answer a question about whether newborns from mothers who smoke weigh differently than, on average, than newborns from mothers who don't smoke. All right. The data is there, right? We have weeks is how many weeks they were at delivery, the weight of the baby, the sex of the baby, and whether or not they were smokers. And again, like it said, the only thing that we're really interested in is the weight and whether or not the mother was a smoker during the pregnancy. That's it. That's all we care about. Obviously, there's 150 data entries, observations. They didn't list them all here. They're going to do the work for you. And here are 2 histograms. So I didn't capture the bottom, but the top is newborn weights for mothers who smoked, and the bottom is did not smoke. Ooh, look at that pen. Didn't smoke. Nifty, but get the hell out of here. All right. And it's hard to make a conclusive decision here, right? The ones that didn't smoke, looks like the peak happens a little bit more to the right. The tail to the left is a little bit smaller in the data set of mothers that didn't smoke. But it's hard to tell here, right? In my opinion, we're going to probably not have conclusive data here to suggest anything. But that's just based on eyeballing this graph, right? So this, we want to all right, give me 2 seconds. My AC like kicked on and it's like 30 freaking degrees in here, so give me 2 seconds. All right, sorry about that, and thank you. So we want to create our hypothesis, right? So the status quo here is that there is no difference, right? So in words, there is no difference. Why am I writing everything? Type. Yoink. Between the weights of babies, of mothers who smoked during pregnancy and those who didn't, right? That's in words what the hypothesis means, right? Get this, just erase this, go away, yoink, yoink, yoink. Right? So that is H naught, right? The alternative is that we think there is going to be a difference. It doesn't suggest that the difference is positive or negative. So our alternative, H naught, is simply that there is a difference between blah, 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 blah. The blah, blah, blah is, of course, the difference between the weights of the babies of the mothers who smoked during the pregnancy and the weights of the babies of the mothers who did not smoke during the pregnancies. All right, so what does that mean? In words, that's all well and good. What I want is in mathematical notation. H naught is then that the mu, the population mean of mothers who didn't smoke minus the mu, the population average or mean of the mothers who did smoke. No difference means that the difference is 0. Right? And so the alternative, once again, because it doesn't describe, we're looking to see if babies are bigger in one or the other. It's just, we want to know if there's a difference. And so then we find our H alternative to be that the difference of these two things, mu sub n minus mu sub s, is not 0. And this is the test we're going to run. We want to check the 2 conditions, right, to make sure that we can run this test. condition 1. Excuse me. All right. Because this data came from a simple random sample, I'm gonna die. You'll see that as SRS, right? This came from a simple random sample. Right. And is less than 5% of all cases, which is, I can't see the numbers because I scrolled away. It was 150 cases altogether. That's certainly less than 5% of the babies that were born in North Carolina in whatever given year this might have been. And so it is, it passes criteria number 1. Right. Criteria. Oh, and the skew is reasonable for these things. We have enough samples that we're not too worried about the skew on those graphs. And then criteria number 2 is that these guys are certainly independent within each group, right? It is essentially the exact same argument that we used in number 1. The number of mothers that smoke while they're pregnant. I don't know that data, but it's South Carolina, so it's probably, all right, now I'm being judgmental, but it's probably certainly less than 5% of that data. And then likewise for those that did not smoke, right? So this passes as well. Excuse me. Okay, and therefore we can then use the t-distribution. So I'm going to grab this data again here, and by again I mean for the first time, and post it. Here is the rundown of the data. We are given smoker category, non-smoker category. We're given the mean, the standard deviation, the sample size. So I can write this in something that I prefer to write it this way in the variables that we're going to be using. So X bar of smokers is 6.78. X bar of the non-smokers is the 7.18. The sample standard deviation of the smokers is 1.43, and the sample standard deviation of the non-smokers was 1.60. So now this data, this summary suggests now that the average weight of the babies of the non-smoking mothers is larger, right? But again, we have to find if that is statistically significant or not. And so N, number of observations of smokers, was 50, and N, the observation of non-smokers, is 100. So I have these 6 bits of data. Okay. And they draw a picture here, which is not always the worst idea ever. Of what we're really looking at. So they've drawn a picture, represents the p-value for the hypothesis test, right? They've drawn essentially the assumption, the H0 suggests then that there is no difference, and therefore that's our assumed mean, or our assumed difference of the means in this. And then this observed difference that we found, or that we didn't calculate this, so back up here for a second. The point value that we got here, or the point estimate, is for mu, let's do this, x sub n, x bar sub n minus x bar sub s is 7.18 minus 6.78, and that is 0.4. So they've drawn that on this normal curve here, this curve. The observed difference is sitting down here at 0.4, and so if I get values to the right of that, values to the left of that, that's the p-value, and I want to figure out if that is larger or smaller than 0.05. So we find our t-value, which is that point estimate. So that's the x, I forget which one's first, n minus xs right, and then minus n minus mu s all over standard error, which we also didn't compute. They have it here. We didn't compute it. Right. So let's compute it. We're going to need it. But we have all of these values in that t equation except that standard error. So let's compute that guy here. The standard error is the square root of, so if you remember, it's s1 squared over n1 plus s2 squared over n2. So I'll throw those values in. Excuse me. This is the square root of s1 would be s, in this case s, right? If you want to write these as in the terms of this problem, it doesn't matter which one is s1 and s2. Right? ss squared, s sub n squared, those values. And s sub s is 1.43. Square it over n sub s is 50. Plus s sub n is 1.60. Square it over 100. And that ends up being, rounded to 2 decimal places, that ends up being this 0.26. Oh man, I could have totally cheated because it is in the book. I didn't see it in the book, but here it is. Every chance I get to cheat, I would like to, but I didn't. It's right there. Okay. So now I have everything in this t equation, xn, x bar sub n minus x bar sub s. This should have a bar over it right here. That is the 0.4 minus, but the difference between the two in the null hypothesis is 0. And then the standard error is 0.26. Right, so this comes out to be approximately 1.54. How many degrees? 49. All right, so when I get my T-chart here, and I pop this sucker right here. The question now is, we have two sets of data, right? We've got N of smokers was 50, and we have the N of the non-smokers was 100. How many degrees of freedom do we have? Because those are two different numbers, right? And so to make these T tests as valid as possible, we have to use the worst case scenario, and the worst case scenario is the smaller N. And so I'm going to use the smaller N to figure out my degrees of freedom. So my degrees of freedom is that smaller value minus 1, so that is 49. So I have 49 degrees of freedom, which means on this chart, we're hanging out right in there, right? Okay. And so this T value that we found, I forgot what it was because it's over there, 1.54. Is somewhere between these two. Let me just get blue. I don't know, blue. 1.54 is somewhere in here, right? So I know that it's between, since it's a two-tailed test, and then we saw this in the last time, it's between 10 and 20%, right? So my T value is somewhere between 10%, 20%, or somewhere between 0.1 and 0.2, right? I don't know what it is. I don't care. What I care about is that that T value is definitely greater than 5%, and therefore I do not have enough information to reject. There's not enough information to suggest that either group has larger or smaller babies, and therefore we can't conclude that smoking in this study has any effect on the birth weight of these babies of mothers of North, South Carolina. And that's it. That's the test. And that's it for this one. There is one more test. I'm almost certain that if you go through that test, it will reject the null hypothesis. Right? And that's what I'm saying here is when we fail to reject, we fail to reject H naught. Right? So starting in the book, there's another example that they go through on page, starting on page 110, they go through the whole thing. If you want to look at that, look at that. If you have questions on it, send it to me. But I am about to die, and I've been recording the last 3 videos just straight, so done. Anyway, if you have questions, let me know, and peace. We're done. And I think that's it for, is that all the videos I said I do? Let me make sure I'm not lying to you before I say goodbye to you. Where is my calendar? There it is. And there it is. And that was 4 point something. 4.2b and 4.3, 4.3b, and that's it. Yeah, so that's all of the videos. That's all of module 4. Let me just make sure again that I'm not lying to you. That is it. Yeah. So that's it. That's module 4. We'll that was a lot. It was very much much more heavily mathematical than we've done in the class up to this point. But I'm glad we took care of next Monday's course in these videos as well. That way, I think on Monday I will bring in some of these examples. We'll go through them in class because this is almost certainly going to be heavily point valued on your next exam. So peace out. See you when I get back on Monday, the whatever-eth that day is. I don't know. I don't know why I would ever suggest that I knew, but that's it. Take care. Bye.